This is good looking work, right or wrong. Aesthetically.
As long as we get points for, neatness, it's awesome.
Oh, then I
You get
wrote it down.
appreciation, I'll tell you that.
Let's say let's not, because we have me in this class.
Yeah, but you get the right answer.
No, I don't. Not in this section.
Are we
Lose-lose.
okay now? I don't know if are we okay?
I think we're okay, but I would like to see anyone on the board, just because it'll help it sink in, I think. You know,
Well, I don't have a number anyone, so
Yeah, so I was just gonna see if
Casey,
there's,
were you still confused on 22? Did you still? I
Let's
know
leave it
what
open
you were
to
asking, so.
whatever number you guys wanted to do.
It's like we know we have it,
Wait,
but
did y'all
then
have any
we're
stipulations for
convinced we
22?
don't.
Not me.
-1.11 is the actual
I
answer.
think
Good timing,
22, I have
Freddie,
this
right on.
number-
Is there a number, Freddie, that you want
Yeah.
to see specifically? Negative 1.11.
Probably everybody was at 28 or something, like, well, we.
Oh, I think we figured that one out,
So,
so.
like,
I would say, I don't know. I don't know, cause I was confused on
So we're good on 19. Let's just,
about
let's
40?
just go through all of them real quick. Okay, so everyone's good on 5. Yes.
Casey's a leader.
I am, man. I put on my big girl
Executive
pants.
ability.
Um,
Run the show.
number 6, I did wrong, which I can go back and do later. But y'all are good on that one?
Mhm.
Yeah, I think so.
Okay, number 9.
Yeah, I think, I see what I did wrong on all of them, I just,
Number 11.
I think I'm good on one.
I'm not answering because I got all of mine
There
wrong,
was
so.
one, which one was it?
Except for 28, I did that one right.
But then on 11, I have to write out that whole thing, right? I have to go through them,
Yeah.
I think I have mine.
so I didn't do that.
14.
Actually,
Everyone's
can we
good?
do 22? Is that okay?
yeah.
Okay, a decision has been made, we will do number 22.
Okay.
22.
Then is my age.
Hey, you got young.
Yeah, you guys inspired me. New sheriff in Hush. In recent years, the town of Newport experienced an arrest rate of 25%. So that means their old records testify that the arrest rate is 25%. And that's an established one, it's been in the town for a long time. The new sheriff comes into town, new gun, and she wants to show everybody up, so she compiles records showing that among 30 recent arrests, she managed to get 30%. So she's claiming that this town should no longer think that the arrest rate is 25%. She's disproved that. So she's claiming that the arrest rate is now greater than what it used to be in the past. In other words, she's made some improvement. So what she is claiming is that the claim is that P is greater than 25%. And what we're testing is whether the performance that she did supports that the 25% is an obsolete number and it should be shifted upwards. So we want to see if we support her claim that the obsolete number of 0.25 should now be shifted upwards, that the department is performing better because of her, goes without saying. So we clearly get the H0, that P is equal to 0.25, and H1 is that P is greater than 0.25, so we clearly have a right-tailed test here. And with a right-tailed test, we are working by default at an alpha equals 0.05. So by default, we have the red zone on the right side of size 0.05. Can you see from your chair back there, or is
Yes,
there
sir.
no blockage? So that's what we're testing. So clearly we need a test statistic. So let's get our parameter list in place. We know that P, the background that we're testing against, 0.25, and her new number, P hat, she's claiming is 0.30, and the number of cases is 30, and that means that Q is equal to 0.75, so we have our parameter list in place. So now let's develop our z-test. Z test is equal to Z of alpha over 2 times P, Q, Z test, I'm drawing a blank.
You have my screen?
Z test is P hat minus P over square root of PQ over N. How'd I do?
Yep.
Thanks. Okay, now, so we do the numbers. It's equal to 0.30 minus 0.25 over the square root of 0.25, 0.75 over 30. So, can someone with the fastest calculator in the class give me this arithmetic? Z test is equal to
Negative 0.11. No, just kidding, sorry. Just
That's
kidding.
not funny.
Sorry, it's a good joke to me. 0.63.
0.63?
Yes.
Okay, so now 0.63, I can eyeball it on the graph so I don't shoot myself in the foot. It's right around here, 0.63. So even now, it's very clear that we're going to fail to reject H0. But let's get the actual number. So what we need is a p-value. So this is the p-value. So we look up in the table for 0.63, and z-value for 0.63 on the left side is
0.7357.
7357.
Yes, sir.
So on the left side, we have 1 minus that, which is 0.2643. What's 1 minus that?
Yes.
0.2643. So clearly P is high, so the null must fly. So we fail to reject H0, true? So result, fail to reject H0, it's too close. Actually, I thought it would be better than that. Results. Fail to reject H0. Okay, so let me double check. We had a Z of 0.63, which is sort of right in the middle. And when it's right in the middle, we're not going to reject anything. We're not anywhere near the reject zone. So we failed to reject H0. So now let's work our way through the lawyer E's. On page 417. Did the original claim did the original claim involve the equal sign?
No.
No. Did you reject H0? No. And so there's not sufficient sample evidence to support the claim that the arrest rate is now greater than 25% in the past. End of problem. Claire? Okay, how many agreed with your own result? Good. So that's an example of how we do them all. Okay, any other comments, remarks, suggestions? Okay, it's time to close the course now. And we're now going to cover our last topic, so we can stow the horses away into the barn. And when we come in on Thursday, we will put this last whiteboard section on the board. We will have test 4, which covers assignments 13, 14, and 15. So I'm now going to present our last topic. Our last topic is known as correlation. Alright. So, let me psych myself up for this. Now, Please tell me what I'm doing.
Making a sine wave?
I learned this in Hawaii. Now what I have here are two variables, two parameters. I have my right hand is one variable, my left hand is the other variable. Notice what the two variables are doing. When one goes up, what does the other do?
Goes up,
When one goes down, what does the other do?
goes down.
So these two variables are totally positively correlated, are they not? They're totally in sync or totally in step. So I'm going to give you a real life example of two variables that are positively correlated. First, let's take the miles per hour that you drive, your speed, just call it your speed. And let's talk about your stopping distance. Now, when your speed goes up, what does your stopping distance do?
Increase.
When your speed goes down, what does your stopping distance do? So you see, these are positively correlated variables. So let's take some actual data. When your speed is 30, your stopping distance is 60. When your speed is 40, your stopping distance is 80. When your speed is 50, stopping distance is 100. And when your speed is 60, your stopping distance is 120. So now what we're going to do is draw a graph of this data. Now generally on the x-axis, we choose the variable that is under your control or is independent. Now which one of these are we going to choose as independent that's under your control? The speed. So we put in our speeds, 30, 40, 50, and 60. And the dependent variable is going to be the stopping distance, and we put in our 60s up to 120. So now I'm going to plot my data points. I have a 30, a 60, a 40, an 80, a 50, a 100, and a 60, 120. So this that is on the board is known as a scatter plot. So this that's on the board is known as a what? Scatter plot. It's known as a scatter plot. Because generally the dots are all over the place. They're really scattered. Next thing I'm going to do is draw the best fit line that I can through the points. Now this didn't come from the data, this is something that I added. And this line is called the regression line. So some more terminology, the regression line. Now, notice that in this special case, all of the data points lie exactly on the regression line. That's very unusual. And this is known as perfect positive correlation, because whenever x changes, no matter where on the line you are, y always changes by the same proportionate amount. So this is perfect positive correlation when all the data points are in the line. We have a variable called r, which is pronounced Pearson's correlation coefficient. We generally just call it r. And for perfect positive correlation, it's equal to plus 1.0, indicating that all points are on the line. It doesn't get any better than that. So let's look at the terminology we've learned so far. We have a two-parameter data set, and each point has two partners. And we break those into an x and a y value. So we have a series of xy points. That's input to a correlation study, a set of xy points. We plot them. That's known as a scatter plot. We draw the best line that we can through the data. It's known as the regression line. And if all of the data points are on the line, it has a perfect Pearson correlation coefficient R of equal to 1. So that's what we've learned so far. But in real life, you don't get perfection. You get me. So in real life, you get something like this. Now, would you testify that in general, you're looking at a correlation that goes up and to the right? In other words, as x grows, in general, y is growing also. So this is roughly a positive correlation because it's uphill. So this is what we call a scatter plot. Now my next job is to draw the best straight line I can through the data. This is known as the regression line. Now, since it's a straight line, it will have the equation of any straight line, y equals mx plus b. How do you remember that from your third grade algebra course, arithmetic course? Y equals mx plus b, where m is the slope and b is the y-intercept, which we don't know m and b at this point. Now, the reason that this is the best line is as follows. If I draw a vertical distance from all the data points to my supposed best line, I have a little set of red lengths. Now, that line is the best line for which the sum of these little red lengths is the least. It's the closest to the mostest. So if you can find another regression line for which these little red offsets sum to a lesser value than this one, then that one is the real regression line. So the regression line is a line for which these little red segments, which are called residuals, sum to the least total sum, is the regression line. Now, this amount of correlation is not perfect because all of the points are not on the line, but it's still positive. So I would estimate this to be around, R is approximately equal to 2.7. It's not 1. So I'd estimate that to be around 0.7. Okay, now, this one's much harder. What am I doing now?
Negative correlation.
Exactly. Are these two variables correlated, Steffi? Are these two variables correlated?
Yes. within
Yes, how do you know they're correlated? Because when you know what one is doing, don't you know what the other one's doing?
Yes.
If this one's going up, this one's going down. This one says yes, this one says no. How many of you know couples like this? Totally dysfunctional, agreed? So this is perfect negative correlation. It's not positive because they're totally out of sync, totally out of step, doing opposite things. But they're very tightly linked because when one goes one way, the other is destined to go the other way. So there's a strong amount of correlation, but it's negative. So let's give you a real life example of some negative correlation. Let's have your speed and your miles per gallon. Everyone know what miles per gallon is? Any trouble? You know what it is? Okay, good. Now, are these negatively correlated? What happens to your miles per gallon when your speed goes up? Boom. What happens to your miles per gallon when you wise up and reduce your speed? Goes up. So these are definitely negatively correlated. So for example, when your speed is 30, then your miles per gallon might be 60. If you take your speed up to 40, then your miles per gallon might be down to 50. If you take your speed up to 50, your miles per gallon might be down to 40. Up to 60, then your miles per gallon might be down to 30. So we can put these on a graph. Now on the x-axis, we're going to put the one under your control, which is speed. So it's going to be our x. So you see we have a set of x, y data points. So let's plot them. On the x-axis, we're going to have 30, 40, 50, and 60. Now on the miles per gallon, we're going to have 30 up through 60. So let's put on our data points. 30 goes with 60, 40 goes with 50, 50 goes with 40, and 60 goes with 30. What is this plot called? A scatter plot. All in favor? Okay, so this is called a scatter plot. Now I'm going to draw a line through the data points. And what is this line called? Regression line. So it will have an equation of the form what? Y equals mx plus b. Now, this is perfect negative correlation because, except for my poor graphics, all of the data points lie exactly on the line, agreed? You don't get that often, but every time you change x here, you will change y by the same proportion, no matter where you are in the line. So this is perfect negative correlation, and it has an R value of equal to minus 1.0, meaning it's a perfect negative correlation. So you see our Pearson correlation coefficient ranges from plus 1.0 to minus 1.0. So it indicates perfect positive correlation down to perfect negative correlation. But in real life, you don't get perfection. So in real life, you're going to get something like this. Do you recognize this to be negative correlation?
Yes.
Because when x goes positive, y goes down. So the next task is to draw a regression line, the best straight line that you can through the data. And that's determined for the sum of the residuals to be a minimum, this definition of the regression line. Now, this is not perfect negative correlation, because all the points are not on the line, but it's not too bad. I would guesstimate it to be about R is minus 0.6 for myself. Now, I'm going to ask you the amount of correlation that I'm indicating on this scatter plot. So please tell me the amount of correlation that is indicated on that scatter plot.
No
Zero.
correlation.
Zero, absolutely right. You say, well, that's impossible. Everything in the world is connected and related. Okay? What's the correlation between the time you get up in the morning and the number of airplanes that take off from Kennedy Airport that day? You'll get something like this, agreed? Absolutely no correlation. So for this we say R is equal to 0. No correlation. So now we have the handout that we're going to use for today. It comes from the Cal book.
Thank you.
Old news to at least one of you. Now, for a high mark in the course, I want anyone to tell me what is the name of the movie that the front piece picture is of. The name of the movie is, Freddie knows. Come on, Freddie, dig. Tony might know from an earlier course. She's grounded, she can't remember.
I know, I'm mad at myself.
Come on, dig, dig, dig. This
Trying to
movie
see
is,
who this is. Who is this in here?
I'm asking you, not
I
you,
don't
me.
recognize any of the actors.
That's right. Who is this in here? Okay, never mind.
Oh,
That's right.
Denise, the movie,
Matisse Falcon, no.
That's not on Audrey Hepburn either.
It's not Audrey Hepburn.
That's the
No,
name I
it's
was
not
thinking.
Audrey Hepburn.
Because you were
Okay,
thinking Breakfast at Tiffany's, and
Yeah.
that is not it.
No.
okay, so you guys off for him. Okay, now let's go to page 727 for our first feedback on statistics. On page 727, you will notice that we have 7 graphs here, 7 scatter plots, agreed? And I'm going to ask you to tell me, as an estimate, the value of R for each one. So you get good at doing that. I'll do the first one myself. A, I'm going to say is equal to R equals 1, a perfect positive correlation. Stephanie, what would you say about B?
A strong positive correlation, R is equal to 0.8.
That's good. Kaylee, what would you say about C?
R is equal to 0.3, moderate to weak positive correlation.
That's awesome. My sheet has the answers, but suddenly I'm not sure. Never mind. Hannah, what about D?
R is equal to 0, no correlation.
Something's going on here. Freddie, what about D?
It appears to be, it might be a negative 0.3, but I'm not sure.
And in
It
words,
was the wrong
Just
page.
a guesstimate.
what would you say in words?
Moderate
Moderate to weak negative correlation.
It appears to be that way.
Casey, you're my last hope. F.
Alright, R is about equal to,
Hush.
okay, negative 0.8, a strong negative correlation.
Okay, Tony, can you take us out with G?
R equals -1, perfect negative correlation.
Okay, so now from this little training, you should be able to guesstimate the value of R in any given scatter plot. So let's reverse pages, and we'll go back to page 726. Now, before we do any talking, I'd like everyone to guesstimate the amount of scatter, the resolution, the value of R for this graph in the margin left. What would you guesstimate R?
Negative.
Negative 0.8? Negative 0.8? Okay, negative 0.8? Good, so we know what we're doing. Okay, I'm gonna say what's going on here. We had a social psychologist that needed to publish a paper, as they often do. So he mused over what he could do for a research project. And he's got to feed his kids, come on, give him a break. So he came up, he said, I'm going to study the correlation between the years of education a person has and the amount of prejudice the person has. Psychologists come up with studies all the time. Now, when he measured prejudice, he wasn't just talking about any specific type of prejudice. He was talking about all kinds of prejudice, just a prejudiced person. Doesn't like black dogs, doesn't like mornings, doesn't like sunny days, doesn't like chairs. A lot of things a person doesn't like, has a high amount of prejudice, agreed? Against a great many things. Now, he set up his data set, X and Y, as the years of education and the amount of prejudice a person has. Now, one of these is under a person's control, supposedly, and that's the amount of education that they get, agreed? So that he designated as the independent variable X. It was easy to measure. It's usually a matter of public record, how much education a person has. So he was able to get that data. He picked 10 subjects, agreed? So he's got 10 XY pairs. Now, for the amount of prejudice, he came up with what psychologists often do, which was a 25-page questionnaire. And at the end of filling out the form, he was able to pinpoint the amount of prejudice that you had on a scale of 1 to 10. Now, these tests are usually pretty good. Much to many people's consternation, they do reveal things about the personality. Steffi's saying, yeah, we've been there, had it done. Okay, so he does get a partner in each case for the years of education to go with the scores in the prejudice test. Now, before we look at any results, I just want to get a gut feel from people in the class. Just as a gut feel, do you think that the more education a person has, the less prejudice they are probable to present? How many say more education would result in less prejudice exhibited? Okay. Now, in general, we come to this conclusion because we say when you start going to university, then you see different ways of looking at things than you were raised to see. You see other viewpoints. You see relative positions. You see students from other cultures. You get other viewpoints that you've never been exposed to. You read books. You listen to wise dissertations from wise instructors. And you see many, many viewpoints that never occurred to you before. You widen your horizon and perhaps come to the conclusion that your viewpoint is one amongst many. So this is a general argument that education reduces prejudice, right? So how many would tend to go along with that? That you can see the value of education reducing prejudice?
In theory,
In theory, okay. Right. There are some hard cases, I know. Okay, now, so what he did was he took his data and he made his plot. And lo and behold, what did he find? That there is a strong negative correlation between years of education and amount of prejudice, just as your gut was telling you, agreed? So he published his results. Now, what should he publish? Should he publish that the data proves there is a strong negative correlation between years of education and amount of prejudice, or should he publish the data establishes that education reduces prejudice?
no.
Second
First-
one.
Oh, the second one?
Which one?
I say the first one.
And we say,
Second one.
how many say second? Freddie wins. Because you can never cross that line. You can never cross that line between correlation and causality. All his data is showing is that when one goes up, the other goes down. It doesn't say anything about which one is causing the other. If he went that far, he would have no foundation for doing it, because there could be many other factors involved, hidden factors that haven't been yet found out to be, confounding factors that could be forcing the results to come this way. So he can only say what his data shows, and that is that the data establishes when one goes up, the other goes down. He cannot say anything about one is causing the other. That would be going too far. And never in research is he allowed to cross that line. And I'll give you an example. As we move now into summer, and we will be, two things will be observed to happen. One, the days get longer. Two, the temperatures go up. Do you agree there's a very strong correlation? As the days get longer, the temperatures go up, a very strong positive correlation. Now, which one is causing the other? Are the longer days causing the hotter temperatures, or are the hotter temperatures causing the longer days? Which is your choice?
He did.
It's the rotation of the earth that's causing the longer days.
Well, Freddie? Then the answer is neither.
Neither.
Neither. But it's tempting to say, naively, that the longer days are causing hotter temperatures because there's more sun coming down, heating things up, true? But our scientific members are quite astute. Neither one is causing the other. Both are caused by a confounding third factor, which is the angle of the sun's rays. The angle of the sun's rays changes. Now I want you to tell me which one of these angles is more energy going to be imparted to the table. If the sun ray comes in at a glancing blow and hits the earth this way, or if the sun comes in direct and hits the earth this way, which imparts more energy to the earth? A direct hit does. So in summer, the sunlight comes in at a more direct angle, and it transfers more energy into the earth, and temperatures go up. And also more of the earth's surface is exposed to the sun, and you get longer days. So you see, if you naively had chosen one to cause the other, then you would no longer have a career, because you crossed that forbidden line. You went from correlation, which you knew about, to causality. Now, you can say, well, that's all well and good for sun's rays, but we know, because we know that education reduces prejudice. So you're just playing a game here when you say that you can't cross that line, because it's quite obvious that education reduces prejudice. Just to play devil's advocate, I'm going to make an argument for the counter viewpoint. And it doesn't matter if you think that the argument is something you agree with, but you just have to recognize that it is plausible. How many of you come from a relatively small town? What's wrong with you? Well, for those of us, me included, who come from a relatively small town, how many of you noticed that in your relatively small town, there were some very opinionated people? Okay. Now, as you near the end of your high school career, and you asked your classmates, are you going to go to university? Like me. You got a variety of answers. Some people say, yep, I'll be there. And other people say, no, I ain't going to any university. And you say, how come you're not going to university? He says, because I already know the answers. Universities are for people that are looking for answers, lost souls. I know the answers. I got no need to go to university. I'm staying here. How many of you had at least one in your high school that you could put into that category, or at least in your town? So these people did not go to the university. So the reason that you don't find prejudiced people on university campuses is not because education removed the prejudice, it's because prejudiced people never went to the university in the first place. So it's plausible, even if you don't agree. So you cannot cross that line without a lot more research and tracing down the confounding factors and establishing them. Okay. So now, what we're going to do is turn the page and go back to 727. And you see that what the author has done is he's drawn his regression line. And that regression line is the one that's closest to the mostest. And that has an equation, y equals mx plus b, where m and b are as yet unknown. Now, we have had on good authority that the value of r for this data set was around minus 0.8. And I find no issue with that, except that we do need an exact number. Now, in order to get the exact number, the only data that we have available to us are the 10 xy pairs. Therefore, we must be able to calculate the exact value of r for the 10 xy pairs. And you can do that with a very simple equation that's on the page 728. Silence.
No,
Simple enough.
so bad, actually.
Look. Oh, this is the equation that's used to calculate the value of r. As you see, its ingredients are only the xy pairs and the size of the data set, which for us was 10, agreed? Now you say, that's a nightmare. It's not. As you will come to testify yourself by 2 days from now. So turn the page to 729 and see how you do it. At the top you have your data set, agreed? 10 points, x and y. So you make a column of all the x values. You okay there? And you sum it. You make a column of all the y values, and you sum that. Now you make a new column, x times y. Okay? And you sum that. You make another new column, x squared, and you sum that. And the last column is y squared, and you sum that. And all of those sums go into the formula at the bottom of the page, along with 10 for n. And if you don't make a calculator mistake, then you get the value for r, which comes out to be negative 0.9, and this is now exact. So this is a calculation that we will make in this course, and you will use this formula. There's an alternate formula that you can use if you want to, but this is the one that we stress as part of the course. The alternate one is in your book as well as this one. Now, let's go back to the regression line. Turn back a page or two. You see it's the line that's closest to the mostest. And you can eyeball it and draw it in. But that doesn't tell you its equation, does it? In order to find its equation, you have to know y equals mx plus b. You have to know a value for m and a value for b. Now, where are you going to get a value for m and b? Well, everything comes out of the data set, doesn't it? So let's go to another page that you're going to love just as well as the others. And this would be page 730. So now what you have here is equations for m and b. Equations for m and b, and they make use of the same columns that you've already made. And you just plug in those sums. And you arrive at a value for m and b. Now in this case, what value did they arrive at for m?
Negative.
So we have y is equal to minus 0.69x. And then what value did they arrive at for b?
11.0.
Plus 11.05. So we have found the regression line, true? We found the regression line. need to touch base with your book. So in your book, we're dealing with chapter 10, the chapter on correlation. And I need to turn your attention to page 555. As you see, they have an equation for the regression line also. And it's y hat equals b0 plus b1x. These two equations are identical, they just have different labels. The handout uses mx plus b, and this one uses b0 plus b1x. So you see that m has become a b1, and a b has become a b0, and a y has become a y hat. So this is the statistics version, and we will use the statistics version in here. When we'll call it y hat, for reasons that I'll indicate in a second. Y hat means it's on the regression line. It's the value of the regression line that matches this x. So if I go to any one of our graphs, then if I take this value put right here, this right here would be its y hat. That is the value of this x that is on the regression line, is called its y hat value. So the parameters of this point right here are x and y hat. So it's on the line. It's not the y value of the data point, it's the y value of the regression line with the same value of x as the data point. So that's what y hat stands for. Now, we come to the moment that we have to address the reason that we did this correlation study in the first place. Because in these correlation studies that we have done, we always have some limited number of data points, agreed? Which means that we're always studying the correlation of a sample. If you wanted to study the correlation of a population, you would have to take as many data points as you had members of the population, agreed? And that's too many. So we don't study correlation in the population. So in the population, we have the same two variables. For example, in the population, we have the variables speed and miles per gallon for all the cars in the whole world, universe, or universes, agreed? But we're not going to measure speed and miles per gallon data points for all of them, so we're going to take some sample. So what was the size of our sample in this study? N equals 4. We took 4 points. So we had a sample size of 4. And when you create your sample, you have your XY points, as this socio-psychologist did. And from the set of XY points, you can calculate a value of the correlation coefficient, agreed? R. Then you have to ask yourself the question, can I project the results of my sample back on to the entire population? Which is what I'm interested in. Can I say that the population follows the same regression line that I discovered in my sample? Can I project it back onto the population? Well, sometimes you can and sometimes you can't. So let's give you an example of sometimes that you can. Suppose the size of the population is 500. And suppose the size of your sample is 499. Would you feel confident that the results of your sample also hold in the population? True? But suppose that the size of population was 500 and the size of your sample was 200. Would you then assume that the results of your sample could be projected back onto the population? Well, you don't know. But you see, there's another factor to question besides the size of your sample, and that is how strong was the correlation in your sample? Suppose you had a sample of 200 and the correlation in your sample was 0.95, indicating a very, very strong correlation. So if you had a strong correlation in this size sample, then would you feel confident to project it back onto the population? So you see, it's a combination of N and R. If you have a high N and a high R, then you can do it. So let's take another one. Suppose have N equals 400 and R is equal to 0.9. Would you feel confident that that held for the population? But suppose N equals 400 and R equals 0.0001. No. So even though your sample is very big, then these variables do not appear to be correlated in your sample. So therefore, they're likely not also correlated in the population. So you don't have a correlation. You cannot go back. So you see, it depends on the size of your sample and the strength of the correlation, whether you are permitted to project your results back onto the population. It's a combination of the two. So let's look at the times that you are permitted to project it back. Now always, when you project it back with a certain amount of confidence. So even when N was equal to 499, and say R was equal to 0.95, were you positively sure at the 100% level that this correlation also holds in the population? No. So you have to give a confidence level. So your confidence level there would be very high. But generally when we project back at two levels of confidence, with a 99% confidence or a 95% confidence. So now in this case, where N is equal to 400, R is equal to 0.9, we might project that back with a 99% confidence. Now, if you're projecting back with a 99% confidence, then what is the amount of non-confidence that you have? Alpha is equal to 0.01, and here alpha is equal to 0.05. So the table that answers for you whether you can project back onto the population or not is the table that's on page 731. So you'll find that table. Now I'm going to ask you some questions. You do a sample, so this is the population. So you do your sample, and you find your correlation, and your sample size is 14, and your amount of correlation that you find, R, is equal to 0.56. I'm going to ask you two questions. Can you project this back onto the population at the 99% level? Can you project this back onto the population at the 99% level? Casey?
No.
No, because look at this cell. What is the threshold value of R? In that cell is the threshold value of R that you must exceed in order to make that projection. 0.661, did you exceed it? You cannot. But can you project this back onto the population at the 95% confidence level?
Yes.
Yes. So you see how this table works. So let me give you another example that might surprise you. I'm going to have an N of 82. And without looking at the table, I'm going to have an R of equal to 0.3, which is pretty low, agreed? Now, do you think this is projectable? That correlation coefficient, 0.3, is closer to 0 than 1, isn't it? So how many of you would say it looks dubious? But if you check the table, you will find that indeed this is projectable. Now, the reason it is because this sample size is much larger than 30, and the statistics are very good. It's exceedingly unlikely that in a sample size of 82, you would have found this much correlation if indeed the correlation wasn't there. If indeed the correlation wasn't there. So if you go up to a sample size of, say, 10,000, even if you find a correlation of 0.0005, then that is statistically unlikely in a population that large. So you can conclude that there is indeed correlation in the population. So this is how you find whether you can project back onto the population or not. Now, if you do your study, and you find in your study that you have found a regression line, and it looks like this, and it has an equation y equals b0 plus b1x, and you want to know whether this same line holds in the population or not. Whether in the general population you can relate x and y for any member of the population according to this line. And if your answer is yes, then you can move the regression line equation from the sample to the population. And to show that you are now in the population, you change the b's to betas. Meaning that this equation has been found to be valid for the population, and it is now present in the population. So if you see the equation y hat, and I forgot the hat, y hat is equal to b0 plus b1x, you know that you're still dealing with the regression line in the sample. But if it's written as y equals b beta 0 plus beta 1x, then you know that the transfer to the population was successful. And it's now valid for the population. So let's go to page 556. And we see the notation for the equation of a regression line. If you're in the population, which is the equation for the regression line? Somebody read it off? Well done. And somebody else, if you're in the sample, what's the equation for the regression line?
Y hat equals B sub-0 plus B sub-1.
Yes, okay, good. Now, the value of finding the regression line is that before you found the regression line, you only had some x's and y's that were in your data table, agreed? Suppose that there were 5 of them. So for any one of these 5 values of x, you knew its partner, agreed? But once you find the regression line, it's good for all x's on the line. So you can find the y partner for any x once you find the regression line. That's the value of it. So let's work a few questions. Now, if you try to read all of 10.2 and 10.3, you will find that I'm only presenting about 25% of it. So I just leave it to your discretion to pick out those topics that I've covered in this presentation and to skip the rest. You're not responsible for the rest. Okay? So let's go directly to the question set. Number 1 on page 567. Number 1. So, Casey, can you read it, please?
Notation and terminology.
Well done.
Thank you so much. Best compliment I've
Hush.
heard my whole life. A physician measured the weights and cholesterol levels of a random sample of
Okay,
men.
could I interrupt? So now we're talking about just a sample, agreed? Please continue, thanks.
The regression equation is y hat equals negative 116 plus 2.44x, where x represents weight in pounds. What does the symbol y hat represent?
And your answer is? It's the value for any x that is on the regression line. For any x, it's its regression line partner. It's not its data set partner, it's its regression line partner. So it's a value of the regression line present above any value of x. Now, as you read the text, you will find out what predictive variable means and response variable means. Now, in what sense, Hannah, number 2, is the regression line the straight line that best fits the points?
It is the line closest to all points on the graph.
Closest to the mostest. Okay, now the sum of the little red lines is the least. And what are the little red lines called?
Residuals.
The residuals. The sum of the residuals is the least. Now, to make the arithmetic easy, because some of the residuals are plus and some are minus, you take the sum of the residuals squared to get rid of the minus signs, an L trick of ours. So it's the least squares fit. It's what is called the least squares fit of all the residuals. Correlation and slope. We skipped that one. 4, notation. So Kaylee, could you read 4 to us?
What is the difference between the regression line, or regression equation, y hat equals b sub 0 plus b sub 1 x, and the regression equation y equals beta 0 plus beta 1 x?
And the difference is,
Y hat is for a sample and y is for a population.
well done. Good. Now we're coming to our first calculation. So you guys go ahead and do number 6 while I just sort of wait. Now, by the way, the y hat value that is on the regression line is what's called the best predicted value. So let's take some x, such as this value of x. It's not on the line, so we don't know what its partner y should be, but its partner from the regression line, from this equation, is our best fit to it. Because the regression line is best representative of the entire set of data.
What's the coefficient, is the grammar? Is that what you said?
No, that's what we're trying to find. Is that x?
That's why I'm lost, I was like, is the correlation coefficient, where do you put that, is that close enough? Or
So
do we put
60 goes in
60
there.
goes where x is, right? So is the
Yes.
coefficient the, maybe that's just extra. So I'll go with.
Doing the most.
So then, did y'all do 63.9?
That's 63.906.
Okay. Just wanna make sure that.
like it, just plug and play.
Okay, sounds good.
So I was like sitting there, what's all the extra numbers, I thought,
Make sure you're writing these down, cause this is homework.
Most definitely is
Oh, yeah.
homework.
no, look, I even know how much.
So you did, you use 60
I did. use
Yeah.
for
it.
X,
So given the height of the mother is 60 inches,
so then the height of the
daughter would be
The 63.9, yeah.
0.6. To be really specific.
Yes, I got the 0.6 on there.
Yeah, I'm with you,
Yay,
'cause I'm calling this late.
class, yay. Field trip.
leave, no, I'm just kidding.
Let's not.
So the linear coefficient is R.
Oh, okay,
Oh,
I'm gonna write that down.
wait, what? The linear. So R equals 0.69.
So then, wait, so do we have to? So do we need to do something on?
No, I can tell you this question.
It says the sample of 8 mother daughter pairs.
So that would be whether or not you could project it back onto population. So if R equals 0.693,
Oh.
it doesn't go above those two numbers, so you wouldn't be able to project it back onto the population.
Yeah, I'm just curious why it says, okay, no, that's predicted value, should follow the prediction procedure summarized in 25.
So I'm not the only one that took a break. So, Kaylee, you have a number.
Here,
Your number is?
63.906.
Inches.
All in favor? Okay, good.
Was that all we had to do, was just the Y-hat?
Not a hard course.
Oh.
We were curious, it gives the linear correlation coefficient, which we realized is R, in this problem. Is that just, they're just giving us that extra information?
At this particular point, let's see. You have to answer the question of validity, okay? In other words, is this regression equation valid? Okay? So is the regression equation valid? So if you go to your equation, your table, and you have a sample of size 8, and you have a linear coefficient of 0.693, then you find that this is invalid, agreed?
Correct.
So you have to have the caveat, there's a little bit of contradiction here, because if the data set is invalid, then the regression equation never should have been created. So the author has a little bit of contradiction here. Okay, good. Now, let's go up to number 5. How many households are there? 62? And R equals 0.759. Does this become valid? Yes, so therefore we can do the calculation, agreed? So let's do number 5 now, put in 50.
So we shouldn't have done numbers.
Hmm?
So we shouldn't have done 6?
I'm not clear myself, so that's the reason I didn't, did I sign it?
Yes, sir.
Right, I would have to further research, the intent of the author.
It just says, it says be sure to follow the prediction procedure summarized in 10.5.
Yeah, but that's,
It does say you found the best predicted height of the.
yeah, okay, now if we do that, we're going to reject it. So let's go to set, the figure 10.5, we're going to have to at some similar point, I was holding it off for a moment. This is when you can predict the value of lines. So is the regression equation a good model? The regression line graphed in the scatter plot shows that the line fits it looks good, right? It looks good. I mean, if it looks bad, then don't use it. So that's just eyeball, visual. But point two, R indicates that there is a linear correlation. So in our case, R does not indicate a linear correlation. So in number 6, we're moving to the answer of that you cannot use this equation. However, if you cannot use this equation, then there is a fallback. So in this flow chart, and who is it in here that loves the flow charts? Okay, now in this flow chart on 559, what is the third bullet? The production is not much beyond the scope of the data. So that's okay, 60 is in the scope of the data. So we have a no. So if you get a no, then what's your fallback? Right. If you have a no, then you can't use the predictor equation. But what you can do, instead of saying I can't do it, is you can just give the mean value of y in the study. Y mean. Now, it's hard to see that that is going to be useful, but that is the prescribed thing to do. So in this case, we would go with y mean. And what is y mean?
63.3 inches.
And that's just what we would send out. So you use this flow chart on every one of these tests, and if you get a no, then your answer is y mean. If you get a yes, then you use the regression equation. So let's do number 5.
So is this the same as the other chart that if it's just close, you just go with which whenever it's closer to?
Yes. So first, do we get a yes or a no?
Yes.
Yes.
Good. So we use the equation. And Hannah, your predicted number of people is?
I think I did something wrong because I got 1.04.
You're right. You did something wrong.
Oh, found it.
The new answer is?
6.395.
I think that's the one we want. Okay, good.
Concur.
Now I'm going to change the problem slightly and ask you to do it again. The last line I'm going to change. What is the best predicted number of people in a household that discards 200 pounds of garbage? 200 pounds. What is the answer?
24.245.
Agreed.
Negative.
What?
Wrong answer.
What?
Wrong answer. How many of you read the flow chart on this problem, as you should read it for every problem?
I did not.
Oh, that's obvious.
Oh.
Number 3. So Stephanie, could you read number 3? Use the regression line on page 559.
The prediction is not much beyond the scope of the available sample data.
Would you say that in this study, 200 pounds was outside the scope of the study? When the mean was 27?
Yes.
10 times the mean? Yeah, so in this case, we use what as our backup?
The mean value.
And the mean is
27.
27, and that's what we use. Okay, good. Now, this table that I passed out to you is in your book. So let's race to see who finds the page in your book that has this table. Hint, it's between 789 and 791.
Okay, I found it.
And the page is?
790.
One, done. So you see, you don't need this handout any longer. We're almost through with it, because now you can use the same table in your book. Okay, now before, we're done with the presentation now. So before I start having you work a sample problem, I want to cartoon you. So let's see if the cartoon is present on this handout, or, yeah, it is. On the very back side. Okay, Kaylee, could you read the balloons in the bottom cartoon? I need help answering.
I need help answering all these questions. Okay, read the chapter, then we'll answer the questions. Read the what?
Okay, that's old news. You guys are pretty good about reading a chapter. You're not homework jumpers. Okay, good. Now, Freddie, could you read the words in the cartoon above it? I used
to think correlation implied causation. When I took a statistics class, now I don't. Sounds like the class helped. Well, maybe.
I hate you people that are laughing right now. I did not catch on to this till the next morning. It's very obvious that some of you beat my time. Now, there's a rule on this. If you're not sure whether you caught on to it or not, then you haven't caught on to it yet. Because when you do catch on to it, you're absolutely sure. Now, how many of you are absolutely sure that you caught on to this? Okay, so where's the hardest problem I can find?
Thank you. Wow.
It was
Just
fun
kidding,
to
I don't
do.
know.
I'm just kidding.
Okay, so let's go to page 549. And let's get you started. I'm going to go to problem number 16 on page 551. Now, before we jump into it, Casey, could you read the instructions for this problem?
Testing for linear correlation.
Okay, Tony, did you locate the instructions? Or did you just start doing it?
No, I'm sorry, I was taking notes to help somebody.
Okay, my bad.
But I
So-
do have the instructions.
Good. Casey, could you read the instructions?
Sure. Testing for a, is that correct? I
Yes,
don't know.
ma'am, you're
Okay.
right place.
You didn't give me a hint.
Hush.
Okay. Testing for linear correlation. In exercises 13 through 28, construct a scatter plot.
Could I interrupt? First thing you do is construct a,
Scatter plot.
go. Second thing.
Find the value of the linear correlation coefficient.
Now, how do you
R.
find that? From our very simple equation, right? With those six columns? Go.
And find the critical values of R from table A6 using alpha equals 0.05.
That's page, what was it, 290 or something?
790.
790, something like that? Then determine, do what?
Determine whether there is a sufficient evidence to support a claim of a linear correlation between the two variables.
Okay, so what you have to do is decide yes or no from the table, right? Okay, so now let's go to page 567. And let's go to number 16. Does this data set looks similar to the one on the earlier 16. That's intentional. It's a follow-up chapter. And you can use the data from the first one in the second question. So in the second question, what are the instructions? Casey, you're doing great. Let's read the instructions to number 16 on page 569.
Find the equation of the regression line and making predictions. Exercises 13 through 28 use the same data as exercises 13 through 28 in section 10.2. In each case, find the regression equation, letting the first variable be the predictor x variable. Find the indicated predicted value by following the prediction procedure summarized in figure 10.5.
Okay, is this a short, simple problem?
No.
Start now. So do both 16s. First the 16 on the 10.2, then the 16 on 10.3. Who's done? So make your columns. Check it twice. Find out what's naughty and nice. Now, you really shouldn't depend on the handout anymore. Let's find the equations in your book that you need, because your book is what you're going to be using. So let's go to page 546. 546 at the bottom. What do you see there?
The R equation.
Equation for R, agreed? Okay, now the next page that we're going to go to is the equation for B and B0. And those are on page 555. So let's go to 555. So those are the equations from the book that you use. You don't use the handout, okay? I was just training you. Yeah.
The chart,
It's those,
the chart is in here.
oh, you want to model the chart. That's a very valid thing to do, yeah. Model the chart. Yeah, Trio is not good at giving you a chart model. How many are glad you're not taking this course online? So Hannah's suggesting that you use this model table from the handout, which is a good idea. Just get your columns straightened up.
For the scatter plot though, since X is supposed to be the one you can control, right?
Well, they indicate here, they call it the predictor. Predictor means independent.
So you can.
So they tell you which one is the predictor. So how is it that they call it? Just read it off. They say the first row is the predictor. In other words, the first row is X.
Oh, okay.
Okay. So, fine. So again, there's a lot more material on these pages than we're using, but the stuff that we need, you do need to know how to locate. guess they don't tell you which one to call X or not, so, in this problem, the heights of precedence, okay, now it's a property of correlation that if you call one variable X and the other Y, and you calculate a value of R, then you do it in reverse. And call the first variable Y and the second variable X, you get the same value of R. So it doesn't matter. It does not really matter. But they do tell you later that they have a preference, actually. When it gets to the regression line equation, it does matter, and in that case, they indicate they want the first row to be X. So might as well start that way. I've ordered the t-shirts, I survived Stat 200. Should be right along.
I would wear that.
I would too.
My friends have survived.
The back of it says hush.
Alright, who's doing it? Who's ordering them?
I would totally do it.
Tony, you're the artsy one. Sonia?